All right, in problem 6 of homework 12, we're given a wheel here with two wheels, coupled wheels, with different forces exerted on each of the wheels. And we asked to find the net torque, assuming that we have a friction torque of 0.39 newtons. So we told that there is some frictional torque, which is equal to 0.39 newtons, which opposes the motion of this system. All right, so just like we talked about for linear motion, friction moves in the opposite of the net motion of the object. So we'll have to find the net direction of these three forces, of these three torques, and that will help us to know what the sign of the frictional torque should be in finding the net torque exerted on this object. All right, so the net torque will be equal to, so let's call this 1, 2, and 3. The net torque will be equal to torque 1 plus torque 2 plus torque 3 plus the frictional torque. And so torque 1 is 30 newtons times the distance, 0.2 meters. Torque 2 is 20 newtons also times 0.2. Torque 3 is 35 newtons times the distance of 0.1. And all of this plus our frictional torque should give us the net torque acting on the system. All right, but you notice I don't have any negatives or positives here, and we'll have to go back here and consider whether the torques are given us clockwise or counterclockwise rotations, and put in the appropriate signs in this equation. All right, so if we say counterclockwise is positive, then the 30 Newton force is giving us a counterclockwise rotation, so that should be positive. The 20 Newton torque here is giving us a clockwise rotation, so this should be negative. And the 35 Newton force is also giving us a negative rotation, so this expression here should also be negative. All right. So we end up with, for these forces here, we end up with minus 1.5 Newton meters. And so since this frictional torque has to oppose the motion of the other forces exerted on the object, since this part is negative, our frictional force will have to be positive. And so we end up with a net torque on this system being minus 1.11 Newton meter. All right, so in the first part of the problem, we actually find the magnitude of tau net. So that would just be the positive value here, 1.11 Newton meters. And we also asked to find what direction the net torque is going. And so since the net torque is negative, and if we define counterclockwise to positive, a negative sign here means that it's moving in a clockwise direction. All right. We'll skip problem 7 and do problem 8. So for problem 8, you're given a set of objects. So mass 1, mass 2, mass 3, and mass 4. And we're told that the ones here have the same big M masses, and these have small m masses. And the distance between this and that axis is 0.5 meters. And the distance between these two masses here is 0.5 meters. And the total distance between this and that mass is 1.5 meters. So you expect the distance between this mass and this axis here to be 1 meter. So that their sum will give you the 1.5. And so we're also told that the axis is right in the middle between these two. So if this here is half a meter, the distance between this here and this axis here is 0.25. And that's split up in here to also be 0.25 meters. All right, so in the first part, we actually find the moment of inertia of all these particles about the vertical axis of rotation. So we have to consider the distances between all the objects and the vertical axis of rotation. So this is 1 meter, this is 0.25, 0.5, and 1. And we're told that big M is equal to 3.3 kilograms, and little m is equal to 1.6 kilograms. All right, so for point particles, I net is the sum of the masses times the radius square. So if the axis is the vertical axis, we'll have to multiply the masses of each of the objects by the distance to the vertical axis. All right, so let's number our objects 1, 2, 3, and 4. All right, so for object 1, its mass is big M. The distance is 0.25 square. And for the other object, its mass is big M. Its distance is 1 meter square. Plus, number 3 is small m, a distance of 1 meter square. Plus the last mass, which is half a meter, also small m. Sorry, 0.20. So 0.25 is this distance here. So this distance here is 0.5, and that, yeah. So 0.25 is this measurement. So over here we should have a 0.5, 1 meter, 1 meter, and 0.5 meters square. So that gives us a total moment of inertia of 6.13 kilograms meters square. All right. In the second part of the problem, we have to find, so this is for the vertical axis, we have to find the moment of inertia about the horizontal axis. And in that case, we'll be looking at the distances between each of the masses and the horizontal axis, which in this particular case is correctly 0.25 meters. So all the objects are 0.25 meters away from the horizontal axis. So I horizontal will be big M plus small m, all that times 0.25 meters square. So it's just writing out this equation except that the R square is the same, so I just factor that out. And that gives us a moment of inertia of 0.613 kilograms meters square.